Hello everyone. Today we will present about the project of stain of perforated upright section in the core form steel for storage lag. Our members are KALYAJUTA, KRITSANAJUTHA, Natchanon, JANTAB, ISSARAYUT, KHEMJHAN. For the background of the project, steel structure have two types. There are hot roll and cold form steel. Hot roll steel is mostly used in general structure. For cold form steel was used in warehouse industry, especially storage lag. Used in conjunction with ISSARAYUT system, with the property of cold form has more advantages such as lightweight, high strength, and easy to installations. Otherwise, cold form used for lag has many perforated on the surface. Then the problem that happening is bucking. In this project, we are focused on stain upright section. With perforated is how effect to the structure. For the objective, the first is to study the standard of cold form steel with AISI and IMI standard that are used as lag in warehouse and used with automated storage. Level system about the ASRS. The second is to analyze and calculate the loading that is appropriate in each side of omega section of cold form steel that are commonly used for the steel lag following the AISI and IMI standard. For our scope, they have three scopes in this project. The first is studying the performance of cold form steel in AISI and IMI by comparing the results. The second is the omega section of various grades of cold form steel are Q235B and G450. In each series have about 90, 100, 110, 120. The last is discussion in terms of market size by the depth must not exceed within each series and thickness of all series. There are 2, 2.3, 2.5, 2.7, and 3 mm. For the expected outcome, this study must be beneficial as a guideline for future testing on the omega sections. And next is can be the reference for the design of steel slag in a warehouse. And the last is show the influence of perforation of cold form steel that are using in steel lag. Related theory, AISI is the American Iron and Steel Institute. That is general standard of cold form steel, and IMI is lag manufacturer institute that depend on perforated steel used in storage lag to realize two main effects about effect of K factor on behavior and effect of holes. For the AISI, it focused in two mains about the nominal load and nominal moment. For the nominal load, had a bucking in three states. The first is factorial bucking state that occur experience a deflection caused by bending of factorial, and also occur in the acid with largest slenderness ratio and the smaller gradient of gyrations. Next is torsional factorial bucking state. In asymmetric section then simulate bending and twisting of member occur at around center of shear. The last is distortional bucking state is a combination of factorial and torsional bucking state and torsional factorial bucking state, which is a mode characterized by rotation of the flank at the flank wave junction in the member with a stiffness element. For the nominal moment, has the three stain section bucking. The first is section stain is the maximum bending moment capacity of the member that is used for the elastic design. Next is lateral torsional bucking stain is the bucking of the factorial member that deflects out of plan was twist at the shear center of cross section. And the last is the torsional bucking stain is a mode of bucking in which the lift stiffener is insufficient to retard the compression flank at the attack web from become unstable.
And this part is the RMI. We have separated into two parts. First part is the effect of K factor on the behavior, and the second part is the effect of hole. The first part, the K factor is the effective length factor, which the IMI standard is recommended in terms of ASD by K phi equal 0.8 and used for torsional bucking, and Kx equal 1.7 used for factorial bucking, whereas the K phi and Kx in RFD is equal 1. The effect of hole. For the hole, in cold form steel that make the structure weak, to know the quantity of member, Q factor is required by testing of stop column and calculate it with equation in chart. So we use this factor to determine the effective area and section modulus according to the IMI standard. For this slide, the methodological, this chart shows the overall planning project that we are studying generally since August to last month. Then we specify the parametric to decide the study about the state of perforated cold-formed steel since November until now. After that, we plan for the next semester to analyze, to create the table and comparison graph to see the behavior of perforation of steel, and can use this table for the design, the structure as well. In this project, we choose the height 150, 210, 330, which the height that we select is come from the widely and popular use in the warehouse industry. And this slide, we want to know the behavior of steel by using 4 series of steel width that have 120, 110, 190. Within each series, it have a various thickness, width, and depth that we show in the slide. And this slide is the strength of steel depends on the steel grade. We select the 2 grades of steel. First one is Q235B, and the second one is G450. And the use strength and tensile strength that already provided in the slide. In this slide, we choose 3 values of eccentric, where it have a E equal 0, E equal 0.005, and the last one is 0.01. That all values were found often in the cold-formed steel research in part of compressive strength.
For the Q factor, we select Q factor from the various research because our group cannot do the experiment test directly. However, for T cases of Q factor, we focus on the popular value from stub column test. For the case 1, we set Q factor equal to 0.85. Case 2, Q factor is 0.95, and the last one, Q factor is 1. For the step how to determine the load by ISI, first, we will compute the nominal load from T buckling modes that they have flexural, torsional, and distortional buckling stress. In effective area, we will calculate the factor of each length that have width of flange, edge, and web, and determine it. Then we use the governed buckling state value, which is the lowest value, multiplied with the effective area to obtain the nominal load. Next step, we will select design of the combination of compression and flexural member to calculate the arrival load. Then compute the nominal moment of T buckling modes that are section strength, lateral torsional, and distortional buckling strength multiplied to the section modulus to obtain the nominal load. In the end, we combine both nominal load and moment to obtain the arrival load. For the step of IMI standard, the factor that add more from AISI, that R1 is the Q factor which used for compute the effective area and section modulus in the part to calculate the nominal load and nominal moment. And the last is the effective length K factor. In the ASD method, Kv equals to 0.8 used for calculate the torsion buckling, and the Kx equal to 1.7 used for calculate the flexural buckling stress. For the LRFD, both Kv and Kx equal to 1. For our expected results, we will compare the result by creating the graph. For the first one is the relationship between the arrival load and section properties such as width, depth, and thickness, which fits the eccentricity of T cases. Second one is the relationship between arrival load and height, which fits eccentricity of T cases also. Next result, we will create the table of design strength for cold-formed steel rack for AISI and IMI as well. After that, we will conclude the overall result of this project. This is our end presentation. Thank you for your attention.